Welcome to CE 3305, and this video is going to discuss the Bernoulli equation. What we'll do here is we'll start with Euler's equation. I'll make some necessary conjectures and assumptions, and we will arrive at something that looks very much like the Bernoulli equation. Then I'm just going to say it is the Bernoulli equation. All right, so let's start with Euler's equation. Acceleration equals gravitational component minus the gradient of pressure. And in Euler's equation, as you recall, we were applicable only for gravity and pressure, and we were neglecting viscous terms. Okay, so let's make some special statements. Let's require that G is equal to minus GK. Essentially, Z is positive up. Okay, so that's a coordinate selection, not required, but it will ultimately allow us to start to make things make sense. So if we look at our coordinate system right now, at least in Cartesian, we have x, y, and z, and we've just required that gravitational acceleration is g downward. What this does is it greatly simplifies the resulting algebra that we're headed for. If that's the case, then rho g minus gradient of pressure equals minus the gradient of P plus rho g z. Therefore, rho times acceleration is minus the gradient of P plus rho g z. Okay, so that one coordinate selection allows us to bring this rho g z term into the gradient operator. Next, we'll require incompressibility. Rho g equals some constant. Doesn't matter what the constant is. This is the incompressible flow assumption or requirement. That lets us play the following game. Rho times acceleration divided by rho g equals minus the gradient P plus rho g z divided by rho g. Perform the indicated algebra, and we have A over G equals minus the gradient of P over rho G plus Z. Now we'll write acceleration in differential form. So acceleration x equals u du dx plus v du dy plus w du dz plus du dt. We've already gone through that. We do it in the other two component directions. Let me remember how to do this. This would be u v w u v w d by dx d by dx d by dy d by dy d by dz d by dz v v v w w w du dt, du dt. All right, next we'll require steady flow. That means that du dt equals dv dt equals dw dt equals 0. So these come off. To do that, the component equations look like the following. 1 over g u du dx plus v du dy plus w du dz equals minus d by dx of p over gamma plus z, where gamma equals rho g. Just a notation convenience here. That's the x component. The y component is u dv dx plus v dv dy plus w dv dz minus d by dy of p over gamma plus z. Z component, 1 over g, is you'll see u dw dx plus v dw dy plus w dw dz equals minus d by dz of p over gamma plus z. Next, we're going to require irrotational flow. And what irrotational flow means is that the curl of the velocity vector is 0. So we need to consider vorticity, which we will talk about upcoming. For the interim, curl v equals 0 means the following. dw dy has to equal dv dz. du dz will equal dw dx. And dv dx equals du dy. Curl, there's a definition in the book. It's it's a cross product of two vector quantities. Now we'll substitute these into the component equations. 1 over g u du dx plus v dv dx, so we're making this substitution here, plus w dw dx equals minus d by dx of p over gamma plus z. 1 over g of u du dy plus v dv dy plus w dw dy. Again, we're making these various other substitutions as minus d by dx p over gamma plus z. 1 over g u dw, excuse me, u du dz plus v dv dz plus w dw dz equals minus d by dz p over gamma plus z. This should be dy. All right, now we're actually going to study a property of these. Recall that y times dy dx is the same as 1/2 dy squared dx. So that's just the a rule from calculus. Using that, we get the following. 1 over g d by dx of u squared over 2 plus v squared over 2 plus w squared over 2. So we're invoking this rule to reduce these terms, and I'm pulling the d by dx term out front just to make it easier to write, equals minus d by dx p over gamma plus z. We'll do it for y and z. I'll just write it here on the next page. 1 over g d by dy of v squared over 2 plus v squared over 2 plus w squared over 2 equals minus d by dy p over gamma plus z. 1 over g d by dz u squared over 2 plus v squared over 2 plus w squared over 2 equals minus d by dz p over gamma plus z. So we now made all the substitutions, observing that the mathematical structure u du dx is 1/2 du squared of dx. All right, now let's rearrange those three component equations. Let me put a little marker here, rearrange. And we have 0 equals minus d by dx of p over gamma plus z plus u squared plus v squared plus w squared over 2g. Second component equation, d by dy of p over gamma plus z plus u squared plus v squared plus w squared over 2g. 0 equals minus d by dz p over gamma plus z plus u squared plus v squared plus w squared over 2g. And let's look at this u squared plus v squared plus w squared. U squared plus v squared plus w squared is simply the magnitude of the velocity vector. So it's essentially the speed squared. Magnitude and velocity squared. A little bit of vector calculus. If velocity equals u, v, w, then velocity dot velocity is u squared plus v squared plus w squared. The speed is the absolute value of velocity vector, which is defined as the square root of v dot v. So the magnitude squared. All right, let's make that substitution. Let's just declare this UVW. We're just going to name it. We'll call this V squared. Okay, it's a scalar, has to be. So it's a scalar quantity. So now let's substitute that into each of these. We'll do it into blue so we can keep track of what we're doing. D by dx, d by dy, d by dz, p over gamma plus z plus v squared over 2g, p over gamma plus z plus v squared over 2g, p over gamma plus z plus v squared over 2g. Okay, that's simply a substitution for this term. They all equal 0. What that means is they're all equal to each other. Therefore, the following can be written. Minus d by dx of p over gamma plus z plus v squared over 2g equals minus d by dy of p over gamma plus z plus v squared over 2g equals minus d by dz of p over gamma plus z plus v squared over 2g. Recall that if dy dx equals 0, that implies that y is some constant with respect to x. So therefore, all three equations have to equal the same constant. So that d by dx of some constant has to equal d by dy of the same constant has to equal d by dz of the same constant. That's the only way this expression can be true. Therefore, we have property that p over gamma plus z plus v squared over 2g equals some constant. Turns out that that looks an awful lot like Bernoulli's equation. In fact, it is Bernoulli's equation. So that was a argument moving from Euler's equation to Bernoulli's equation. Let's summarize the conditions that happened for that to be true. Was steady, incompressible, non-viscous flow. With that, we went from Euler's to Bernoulli's. Your textbook takes a different approach to come up with the same result. By all means, you should read the textbook approach. Other important things we did. We used the following principle of calculus. D by dx equals a constant, d of squiggle dx, if that's equal to d of squiggle dy, equals d of squiggle dz equals 0. That implies that squiggle equals some constant. And squiggle in our case was the p over gamma plus z plus v squared over 2g. Okay, Bernoulli's is often written along a streamline. Or in an irrotational flow field as the following. P1 over gamma plus z1 plus v1 squared over 2g at one point in the same streamline equals p2 over gamma plus z2 plus v2 squared over 2g. And that's a very valuable rule. So let's consider a streamline. We'll use blue. Here's my light blue. So this light blue is representing some streamline. We'll measure z in that direction, x in that direction, and then the streamline coordinate Here's point 1, here's point 2, and what Bernoulli's equation tells us is that at this location, P1 over gamma plus Z1 plus V1 squared over 2G equals some constant. This location equals the same constant, P2 over gamma plus Z2 plus V2 squared over 2G equals the same constant. Since Z changed in the way I just drew it, we have a change in delta Z. Z1 and Z2 aren't equal. So the only way that these things can equal the same constant is the V1 squared over 2G term has to change moving from 1 to 2, and or the P1 over gamma and P2 over gamma have to change from 1 to 2. Okay, so that's one of the both confusing and important parts of Bernoulli's equation. The total thing doesn't change moving along the streamline, but the little parts that make up that constant can. And that's very valuable because we can use that to examine flow in pipes and flow in other particular situations. So I'm going to terminate this video, and then the next one will be a series of examples applying this Bernoulli's equation that we've just developed.